The essential starting point for an FEA stress analysis is a good understanding of what results to expect, either from prior experience with similar structures or from a thorough estimate of the stresses. We can then use FEA to get more exact figures for the deflections and stresses, while using our general idea of the expected result as a reality check on those figures. In this video, we're going to learn several simple ways to make careful estimates that will enhance our understanding and use of FEA. Let's spend a moment talking about how a tensile structure reacts to loads in general. As our model for this discussion, we'll use a simple 120-inch by 240-inch barrel vault roof between two arch supports with cables on the bottom edges. A tensile structure's shape is maintained by the balance of two hoop stresses along the principal directions of curvature. These are shown in blue and green in the drawing. The hoop stresses are the result of pre-stressing the structure by means of compensation and also of the structure's specific shape, which determines the size of the two hoop radii. When loads are applied, this could be wind suction, snow load, or any other natural stress applied to the structure, the load causes one of the hoop stresses to increase and the other to decrease. This change in stress will stretch or shrink the material, giving it a different structural shape. That, however, is a further complication which we'll ignore for now. At some load value, the structure will lose all hoop tension in one direction and will then behave, locally, as an inflated structure. This could be the point where large deflections start. The pre-stress value, which is determined by the amount of compensation applied to the fabric at an earlier stage, is the main value that determines how the structure reacts to loads. A high pre-stress results in a stiff structure that will resist applied loads with low deflections, but will need a strong material and supporting structure. A low pre-stress results in a structure that will deflect more with loads, but can be built with a weaker material and supporting structure. The key point is that whenever an external load is applied to a tensile structure, it will increase the fabric stress in one direction and reduce it in the other. Note that fabric stress is always measured in lineal stress, which is pounds per running inch. 2 pounds per inch is a common pre-stress value. Now let's talk about how to estimate structural stresses. An estimate of the pre-stress required to cope with the applied pressure of an external load can be obtained from the cylinder stress equation. The equation goes like this: hoop radius times pressure equals skin stress. The hoop radii of the meshes will be reported by MPanel and can be found using the info tool on the mesh in question. Thus, if we have, for example, a hoop radius of 203 inches, shown here, and if for pressure we have a wind suction of 0.04 pounds per square inch, which is equivalent to a 45 mile per hour wind, then we multiply those two figures, and that gives us a membrane stress of approximately 8 pounds per inch. Since the membrane is slack in the other hoop direction, this is the membrane stress required to resist the suction load. With a larger load, we would expect parts of the structure to become inflated with larger deflections. If we're using cable edges, we also need a way to determine the necessary cable tension. There's another equation to estimate cable tension. We get it simply by multiplying the skin stress by the catenary radius. As you can see in the next diagram, the catenary radius is the radius of the circle we get by extending the cable edge of the barrel into a full circle. The catenary radius will be reported by MPanel and can be obtained by using the info tool on the 3D poly representing the cable edge in question. Thus, if we had a skin stress of 8 pounds per inch and a catenary radius of 124 inches, we would need a cable tension of 992 pounds. The main structural reactions will be at the corners from the cable, plus a load from the membrane stress, which is distributed on the supporting frame. These can be easily calculated. We now have a decent working knowledge of what's actually involved in a stress analysis, and we've developed several estimate values along with a general idea of what kind of outcome to expect from the program, which we can use to evaluate the FEA results.